Hello everyone, welcome to the last video of this week, and this will be a tutorial on how to implement the EM algorithm examples that we have seen in the last videos. So let us start with the toy example that we have seen when introducing the concepts of the EM algorithm, and the context was that we had two observations, y1 and y2, from an exponential distribution with parameter theta, and y1 was observed and its value was 5, and y2 was missing, and after our calculations we arrived at this expression. And just an aside comment, we know that at convergence theta t converges to theta t plus 1, that converges to theta hat, say to our final estimate, and this can be shown just doing the calculations, replacing here theta t plus 1 and theta t by theta hat. This can be shown to be 1 over 5, and this is because this is a very toy example, and I've made this point. We do not need to rederive the E and M steps. We have just this updating equation, but nevertheless, as practice, let us code it. So we need an initial value, and any value greater than 0 should work. Then we need a stopping criterion or a convergence criterion, and I have used the one that we have used also for the numerical methods for the MLE, that the absolute value of the consecutive difference of two iterates is smaller than epsilon, and we specify epsilon. It needs to be just a small number, so they are the two consecutive iterations. They are as close as we want, and we specify it through epsilon. Okay. And as in the numerical methods, basically I've created a function. This diff variable is just for controlling the convergence criterion. So we will iterate until the difference between the absolute value of the difference of consecutive iterates is smaller than epsilon. So as I have said in the video about the numerical methods for MLE, any value of diff greater than epsilon would work. And again here, I theta 0 is my initial estimate, and then I'm saving it in the variable theta that I will be overwriting, and I'm using theta alt to save the value of the previous iteration, so that then I can compute the difference between the estimate in the current iteration and in the previous iteration. And here, this is nothing more than what I have here, our updating equation. Okay, and if I run, yes, 0.2, and we have used a quite distant value, right? We know at this point we have used 10, so we have been told that it's a good practice to start. Of course, if I used a more distant value and it worked well, because here I know that the true value of the estimate is 1 over 5. So let me just run it again, and yes, and hopefully I haven't tried this before, this will not be problematic, but no. Okay, so several different starting values, and they all converge to the same value, zero point 0.2, and which we know it's the correct value. So now for the genetic linkage model example, the one that was used by Rubin, Laird, and Dempster in their original paper. And remember that the context was that we had multinomial data. So initially we had 4 categories, and with some probability for each category that depended on theta, and then we subdivided the first category in another 2 categories, and we applied the EM algorithm. And so this was our Q function for the E step that depends on this Z of t, and Z of t is given by this. And then we have for the M step our updating equation for theta. And if we want to code this, I've coded it in the same fashion as in the previous example. Here, what I'm passing to the function is the data, theta 0 and epsilon for the convergence criterion. I'm saying that n is the sum of the y's. It appears here. And I'm saving in theta, the variable theta, the initial value, and then it's exactly the same thing. Here I have z of t, sorry, for the e step, then I have the m step, and we will cycle, and let's run the function. And I obtained 0.63, which if you do the calculations of the observed data likelihood without the EM, if you arrive at the MLE estimate, it's the value that you will obtain. And if you compare, if you go back to the original article of the authors of the EM algorithm in 1977, this is the value that they have obtained, and we have tried as initial value 0.5. Remember that theta is between 0 and 1, so an initial value between 0 and 1 should work. If I don't have, yes, let me try a more. Yes. So finally, and this is very similar to the first example that we have seen for the incomplete univariate normal data example, where we had one variable. Observations follow a normal distribution with mean mu unknown that we want to estimate, and sigma square the variance we assumed it to be known, and we are under the context where we assume that the first m observations are available, are observed, and the last n minus m are missing. And we have seen last week that in the assuming ignorability, we can just work with the likelihood of the observed data, so just work with the first m observations. And here we have used the EM algorithm, and this is the updating equation that we have obtained. Again here, because it's too simple, we do not need to rederive the E and M steps. We have just this updating equation, and in fact, if we use a similar trick to, as in problem, or as in the first example, at convergence, I know that mu of t converges to mu of t plus 1 that converges to the estimate, to the MLE estimate, and so a fixed point is, if we can replace everything here by mu hat, we obtain the mean of the observed values. And this is what we have obtained before. Here it's a lot more work. I said don't be deceptioned, because the YAM algorithm is useful, and next week we will see in fact the examples where we need it. But okay, nevertheless, let's implement this, and it's exactly the same function. And here I have simulated data. So basically what I have done is that I have simulated data from a normal distribution with mean 3 and variance 1. So we know that our estimate needs to be close than 3. We only have 200 observations, and we will impose missingness. So it's not a lot of data, but we know that we shouldn't obtain 10 or minus 5. And to impose missingness, I used mcar because it's just one variable. So if missingness depends on why, it will be missing not at random, so it needs to be missing completely at random. And I've just randomly picked up 20 individuals, and I have removed these 20 individuals from my analysis. And if I do this and I run, so this is the value that I obtained, and I know that the true value is 3. And then I have compared with the what we have from maximizing the observed data likelihood, or the fixed point of our updating equations, and it's exactly the same thing. Okay, so that's it for these simple examples. Even for more complicated examples in terms of code, we can follow the same structure. As we will see, conceptually, and as I have mentioned, and I think you can appreciate it by now, the two steps of the YAM algorithm, they are at least conceptually easy. But in fact, in the each step, computing the expectation depending on the problem might not be easy, and there are then fixes for it, like computing the expectation by Monte Carlo methods. But In terms of code, it's more or less simple. We might have some trouble in computing the expectations, and we might need to look for something else. But then once we have done that something else, our code is not very different from what we have here, or from there is a lot of, as I've said, in terms of programming. I try to code things as simple as I can, so there is obviously lots of room for improvement here. And I'm happy if you come up with better versions and can email me. I happily receive them. Okay, without further ado, enjoy your week, and I see you on Wednesday online or on campus. Thank you.